Okay, we're in chapter 12, sorry. Still, we're looking at properties of gases and behaviors of gases. And we're in the third video now. And in the third video, what we're going to discuss is some of the gas laws. So you've probably heard of a gas law before because they're studied in physics, they're studied in chemistry, and you even talk about them in biology classes, believe it or not. So we're going to look at those gas laws. The first gas law that we're going to look at deals with the pressures of gases specifically, only pressures of gases, which we just finished talking about in the last video. And this is called, the law's name is Dalton's Law of Partial Pressures. And by the way, for all of these laws, I want you to know the names of the laws as well. So if I give you an equation, that's fine, but can you tell me what the name of the equation is? So what does Dalton's Law of Partial Pressure say? Dalton's Law says the total pressure of a mixture of gases is the sum, that means we're going to add things together, is the sum, my computer's going crazy, is the sum of the partial pressures exerted by each gas in the mixture. What does that mean? Okay, now, the first thing I'm going to say is if you ever add pressures of gases together, make sure you're using the same units, okay? You don't want your units to be atmospheres over here, millimeters of mercury over here. So always use the same units. So practice those conversions that we've been talking about. But let's say that you combine a whole bunch of gases together and you mix them together. The individual pressures of each of the gases inside of that mixture equal the total pressure. Alright, so I've got an equation for you. PT, the total pressure of a gas mixture, equals pressure of gas 1 plus partial pressure of gas 2 plus partial pressure of gas 3, and the ... stands for yada yada yada, meaning however many gases there are in that mixture, that's how many times you're going to add their partial pressures together. It doesn't matter what unit you're going to use for this law. Some of them it will. But for this, it doesn't matter what the unit of pressure is. It could be PSI, it could be atmosphere, millimeters of mercury. However, all of the units need to be the same. So let's do an example. The example here says a sample of oxygen is collected over water at 22 degrees Celsius in 762 torr. What is the partial pressure of the dry oxygen? The vapor pressure of water, this is the pressure of the water over the water, is 19.8 torr. Alright, now hopefully you already read about this in your book, so I'm not going to explain this example to you because there's a whole section in your book that explains what's going on here. And so basically what we have two different gases in our mixture. We have a gas that has oxygen in it, and we also have water, the gaseous form of water. And we're asked what the partial pressure of the oxygen is in the mixture. So here we have the pressure of the mixture of the gases. And we know that there's two gases in this mixture. There's the pressure of the oxygen, the partial pressure that adds to the mixture. And there's also the partial pressure of the water vapor. Okay, that is the gas above the water or the water gas. Alright, so we are asked to find what now? We are asked what is the partial pressure of the dry oxygen. So oxygen without water in it. So this oxygen has become wet, it's got water vapor in it. So we don't want to know what the mixture is. We're given the wet oxygen's pressure, or the mixture of the gases. We know the pressure of the mixture combined is 762 torr. We also know the pressure of the water. The vapor pressure of water is 19.8 torr at the same temperature. So we have 19.8 torr for oxygen, or for water, and we need to calculate the partial pressure of oxygen here. So notice that in this example, both of our units are the same. So we have 762 minus 19.8. So what will be the pressure of the oxygen? Well, if we subtract those two, I'm going to erase it here. 762 minus 19.8 with the proper significant figure. So the one place, the pressure of the oxygen is 742 torr. All right? So the sum of the partial pressures equals the total pressure. If you know the total pressures and all of the pressures except for 1, you can figure out what that partial pressure is. Okay, so we won't spend too much time on Dalton's Law because it's pretty straightforward, right? All right, so now let's move on to what we were going to call the traditional gas laws. And we're going to study quite a few of them. They all relate pressure, volume, moles, and temperature in one way or another. And we're going to look at each law separately, and then we're going to combine some of the laws together. I'd like you to be able to relate the equations with the names of the laws. So know what the names of each of these equations or laws are. The first law we're going to look at is Boyles Law. Boyles Law relates volume and temperature. So it relates the volume of a gas to the temperature of a gas. And that's Charles' Law. Boyles Law relates the volume of a gas with the pressure of a gas. So the volume and the pressure of a gas. And Boyles' Law states that the volume of a gas is inversely proportional to its pressure. The volume of a gas is inversely proportional to its pressure. What does that mean? Well, inversely proportional means if one of the variables is changed in one direction, the other variable is changed proportionally in the opposite direction. So if you increase, let's say this. So what happens to the volume if you double the pressure? If you double the pressure, you half the volume. Another example, what happens to pressure if you double the volume? If you double the volume, you half the pressure. Okay, so if you double something, you one-half the other. So they're inversely proportional to one another. They are the inverse of one another. So Boyles' Law relates volume and pressure. So what is Boyles' Law? Well, if you hold temperature of a gas and moles of a gas constant, so temperature is constant and the moles, or the number of atoms or particles or molecules of the gas, is held constant, then the volume and pressure are going to change inversely proportionally. So there's always going to be a before the change and an after the change for the gases. So we have an initial set of conditions for a gas before it changes, and then we have the final set of conditions after the gas has changed. So that's what we're going to look at. The equation for Boyles' Law is P1V1 equals P2V2. The pressure and volume of a gas multiplied equals the pressure and volume of a gas multiplied. What do the 1 and 2 mean there? The 1 are the initial conditions of the gas. So the initial pressure and the initial volume of a gas before some change. So let's say that the volume changes. Well, that's going to change the pressure inversely proportional. So you'll have a new set of conditions. If the volume changes, the pressure also changes if temperature and moles are held constant. So we're going to use this equation. If you want to read more about what it means to be inversely proportional, go in your book and look at some examples. Because I'm trusting that you read your book first. That's always, you bought the book, you should read it, right? So go ahead and read about what Boyles' Law means. There's some great images in there that I can't use by copyright laws and stuff, I guess. So read your book. There's some great examples. All right, so let's look at some examples of how we use this equation. Now, for Boyles' Law, if you're given initial pressure or volume and you're asked to calculate either a final pressure or volume, well, you don't have to use any specific units. However, the pressure units and the volume units must equal themselves. For instance, I can't use milliliters for my first volume and use liters for my second volume. They've both got to be in the liters or the milliliters. Same thing's true with pressure. The units need to be the same. You can use atmospheres or millimeters of mercury, but they need to both be the same. So let's look at the first example. It says a sample of argon gas occupies 500 milliliters at 920 torr. calculate the pressure of the gas if the volume is increased to 937 milliliters at constant temperature. Okay, now, what do I do when I read these word problems? Do you remember I always reread them? The first time I read them, it's just kind of for a formal exercise. But when I go back, I'm always going to read the problem again. And for the gas law problems, I like to make a list of all of the variables that I'm given and what I need to find. So as I read, I'm going to make a list. It says a sample of argon gas. So, by the way, we know we're looking at a gas, so we're probably in our gas laws chapter. Occupies 500 milliliters. 500 milliliters is a volume unit. So I've got a volume of 500 milliliters. Okay. At 920 torr. So we've got a pressure of the gas, because torr is a gas unit, of 920 torr. Let's keep reading. It says calculate the pressure. Now hold on. Didn't we just get the pressure? Oh, this was the initial volume and initial pressure. There's going to be a change in volume. So it's asked me to calculate the second pressure if the gas volume is increased to 937 milliliters. So I've got a second volume here. The second volume is 937 milliliters. Okay, so how do I know I'm going to use Boyles Law, by the way? Because in this section, we actually are looking at Boyles Law, so we're doing a Boyles Law example. But what we're going to find is that there's actually several different gas laws. And you're going to have all these word problems. How are you going to know which equation to use? The answer is kind of simple. If you make a list of all the variables given and needed in your word problem, you can very easily match which law will match the equation you're going to need. We know Boyles Law is P1V1 equals P2V2. Okay, so let's substitute everything in. First of all, are our units the same? Notice for volume we've got milliliters and milliliters, so those are the same. We're given pressure in torr, so it doesn't tell us what to measure in, so we're going to probably calculate our second pressure in torr. So we're asked to calculate P2 here. The first thing I like to do before I add in my numbers and units is rearrange the equation. So I'm going to rearrange for P2 using basic algebra. And I won't do this for everyone and show you every step. But remember how you do algebra. You isolate the unknown, which is P2. So out here I'm dividing both sides by V2. When I do that, I get that pressure 2 equals P1V1 over V2. So that's what I'm going to start with. So I'm going to say P2 equals pressure 1. I'm going to insert that. What is pressure 1? 920 torr. Now what's my V1? My volume was 500 milliliters. And I'm going to divide that by V2. Okay, so my second volume was 937 milliliters. All right, now, before I go and pick up my calculator, I'm going to do a unit analysis. I've got a milliliter on top, a milliliter on bottom. What units am I left with? I'm left with torr. That's going to be the units for my second pressure. So I've got 920, 3 significant figures, times 500 divided by 937. Make sure you can do this in your calculator correctly, okay? Because I'm going to move on. And when I add all this, multiply and divide together, it looks like 3 significant figures, I get 491 torr. Okay, 491 torr. That will be the new pressure. Now, let's see what happened here. Didn't we say that the volume increased? Yeah, the volume went from a smaller volume to a larger volume. Remember for Boyles Law, we said volume was inversely proportional to pressure. That means if the volume increases, what should happen to the pressure? It should decrease. Is that what happened? Well, our initial pressure was 920 torr. Our final pressure was 491. Did the pressure decrease? It did. As volume increases, pressure decreases. That's a good way to self-check your answer because a lot of times when you rearrange the equation or start your algebra to solve for your unknown, you'll make a mistake. And that mistake can easily be identified by seeing if your answer makes sense. All right? Okay. Now, for the sake of these little lectures here not lasting forever in a lifetime, I'm not going to sit here and solve multiple of the same problem. But if you'd like to try some more Boyles Law problems, here's 2. You can press pause. You can work on them. They're all Boyles Law. And see if you get the right answers. So I'm going to give you the answer. So if you don't want the answer, press pause. Okay, here's the answers. For the second one, a 6 milliliter sample of gas at 8 atmospheres is compressed 4 liters. So the volume gets smaller. What's going to happen to the pressure? The pressure got larger, right? When you calculate this out, what's the pressure of the gas? You should get the second pressure equals to 12.0 atmospheres. And that's with the correct number of significant figures. So see if you can get that one. All right, the third one, a 400 milliliter sample of gas, so that's our volume, is at a pressure of 760. The temperature remains constant. That just means don't worry about it. What will its volume be at 190 torr? What's changing here? The pressure's changing. We're going from a high pressure to a low pressure. As pressure decreases, volume should increase. So our volume that you're going to calculate when you go and get the answer, which you will do because you love chemistry and you want to do so well, you're going to practice. The volume you're going to calculate will be with 3 significant figures, 1.60 times 10 to the 3rd milliliters. Or 1.6 liters, right? 1.60 liters. All right, that's with 3 significant figures, so it might have been rounded a bit. Okay? All right, let's move on to the next gas law. And our next gas law is Charles' Law, so make sure you know the names. Now, what is Charles' Law? Remember, gases have all these different variables that we can measure, and they're dependent on one another. If we were to hold the pressure and the moles of a gas constant, as you change the volume, the temperature will change. Or if you change the temperature, the volume will change. So Charles' Law relates the volume of a gas with its temperature. Charles' Law says that volume is proportional to temperature. Now remember what proportional means. It means they move in the same direction by the same amount or quantity or ratio. So if I were to double the volume of the gas holding pressure and temperature, or pressure and moles constant, if I double the volume, I would double the temperature of the gas. If I halved the volume, I would halve the temperature of the gas. So they move in the same direction. They're proportional. So what's the equation I'm going to use for Charles' Law? Charles' Law equation says you have an initial set of conditions, there's a change in volume or temperature, and then you'll have your final set of conditions. The proportionality ratio, or equation, is that volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. So this equation is the equation for Charles' Law. Volume 1 divided by volume 2 volume 1 divided by temperature 1 equals volume 2 divided by temperature 2. Now, how do chemists usually read this? V1 over T1 equals V2 over T2. That's how a chemist would say it. It's a lot easier to say too, isn't it? All right, now, let's take this to the extreme. Let's say that we lower the volume all the way down to as low as temperature can get. What is the lowest temperature you can have? It's absolute 0, right? Absolute 0 would be 0 Kelvin. Can you have a number over 0? Can you divide something by 0? No, you can't divide anything by 0. That would be an undefined value. So what happens if the temperature gets to 0 Kelvin? How are we going to measure the volumes of our gases if we have an undefined ratio? Well, that will never actually happen. Because remember, at absolute 0, that's the temperature at which there's no thermal motion. And if there's no thermal motion of any particles, or subatomic particles, then your particles aren't moving. And if your particles aren't moving, do you really have a gas, and can you use the gas law? No. If nothing's moving, you only have solids, and the gas laws don't apply. So, even though the volume of an ideal gas at absolute 0 would be undefined, that doesn't happen because we never get a gas at 0 Kelvin. So remember, real gases condense at their boiling point. It's not possible to have a gas with no or undefined volume or at 0 temperature, 0 Kelvin. That would be impossible. Now, so don't worry about that. The other thing I want to mention, is that when you use a gas law, any gas law in this chapter where we're using temperature of a gas, so V1 over T1 equals V2 over T2. Whenever temperature of a gas is involved, you're always going to use the Kelvin temperature scale. Why is that? It's the only scale that doesn't have negative values. If you use the Celsius scale, for instance, first of all, it doesn't work, but second of all, if you did use the Celsius scale, what happens below 0 degrees Celsius? You become negative. When you start introducing negative terms into an equation, you could end up with a negative volume. Now let's think about that for a second. Can a gas occupy a negative amount of space? Maybe in a theoretical world somewhere in some black hole where you have antimatter and all. Oh, that would be crazy, right? No. Matter occupies space. It's the definition of matter, right? It has a mass and occupies space, or has a volume. So we can't have negative volumes. So in order to, first of all, just to negate that fact, we're always going to use Kelvin, because the Kelvin scale only has positive values. No negative temperatures equals no negative volumes. So all of your gas problems, I don't care which one it is, if there's temperature, you're going to use Kelvin. So to remember how to calculate Kelvin, if most of the time in the lab we use degrees Celsius, right, because we've got our little thermometer there, we can convert Celsius to Kelvin very easily. Remember, Celsius plus 273.15 equals Kelvin. So just add 273.15 to your Celsius and you'll always get your Kelvin temperature. Alright, so let's practice a Charles Law equation. Charles Law problem. So here, this example here says that a 2-liter helium balloon at 25 degrees Celsius is taken outside on a cold winter day. So you got this balloon, it's taken outside in the cold at negative 15 degrees Celsius. What will the volume of the balloon be if the pressure remains constant? That sounds like a question, doesn't it? Well, what's the first thing we're going to do? We're going to reread the question, okay? Because I honestly can't remember what I just read. So let's read it again. And the second time you read a question, you're going to take stock or write down all the variables or knowns and unknowns that are given. So you're going to write down all the things that are given to you and all the things you need to find. So the first thing I see is it says a 2-liter helium balloon. I'm going to write that 2 liters down. Liters is our volume, and I know I have 2.0 of them. So there's 2.0 liters. The balloon is at 25 degrees Celsius. Hey, 25 degrees Celsius is a temperature, right? So I've got a volume and a temperature given. It says it's taken outside on a cold winter day at negative 15 degrees Celsius. Hold on. We have a second temperature. So this must be our first temperature because now we have a new set of conditions. Negative 15 degrees Celsius. It says, what is the volume of the balloon if the pressure remains constant? Now, by the way, when something remains constant, that means don't worry about it. So the fact here is that we want to know what the new volume of the balloon is after the temperature has changed. So the temperature has changed. We want to know how the volume is going to change. Temperature, volume. Hey, that's a Charles Law relationship. Charles Law said that volume is proportional to temperature. What happened to the temperature here? The temperature got lower. So what should happen to the volume of the balloon? The volume of the balloon should get less. And this is actually true. This happens. So we should see the balloon shrink, or the volume of that gas inside of the balloon gets smaller. Now, what will the volume be? We've got to calculate it. So we're going to use Charles' equation, Charles' Law. So Charles' Law says V1 over T1 equals V2 over T2. Now, what was our unknown here? Our unknown was volume, 2. So I'm going to rearrange this equation using my common algebra skills that I'm so awesome at here, and I'm sure you are too, I'm going to multiply both sides by T2. So I've got a T2 over T2. I'm going to put a T2 in my numerator. So now I've got that volume 2 equals T2 V1 over T1. So I've just used my common algebra skills to rearrange this equation for V2. Alright, now let's solve the equation. The first thing I notice is that I have temperatures. The first thing you do if you ever have temperatures is you put the temperatures in Kelvin, if they're not already in Kelvin. I notice they're in degrees Celsius. So temperature 1, 25 plus 273.15, what will that equal? And by the way, let's just use 273. It's perfectly fine if you use that. On the test, I'll give you 273. So if you add 25 plus 273, we get 298 Kelvin. So T1 is 298 Kelvin. T2 is negative 15. So 273 minus 15, what will that give you? That'll be 258. Alright, so now we have to use these new temperatures, which are just converted temperatures, in our equation. So now we just plug in what we've got. Second temperature, T2, is 258 Kelvin. What is volume 1? Volume 1 was 2 liters. And we're going to divide that by temperature 1, which was 298 Kelvin. Okay, now remember, before I pick up my calculator, I always like to cancel my units. So my kelvins cancel, and I'm left with liters, which is what I should be left with because I've got V2 in liters. So 258 times 2 divided by 298, calculate. I get, with two significant figures, because that's the least amount there, 1.7 liters. So the volume of my balloon shrunk. It started out 2 liters, and when the temperature decreased, so did the volume, to 1.7 liters. Alright, so that's how you would actually use Charles' Law. So I could sit here and beat a dead horse and do this over and over again, or you could realize that these are just examples of the same problem. So I would suggest you trying some of these problems now. So I'm going to give you the answers, but if you want to solve them first, go ahead and press pause. Work the problems and see if you get the right answers. So the answer here is A. The volume of a gas increases when the temperature increases and the pressure decreases. That's actually combining both of Boyles' Law and Charles' Law, things we've looked at so far. So you can go back and look at the theory. Let's get to the answers here. In this next question that's given here, you're going to be calculating the second volume of the gas when the temperature changes. And as the temperature changes, the volume will change as well. Your volume should be 214 milliliters, give or take how you round. So that many, 3 significant figures. Alright, in the very last problem, if you solve it, you're going to be solving for the second temperature, and I would actually really suggest that you go ahead and try that problem, because T2 in the original equation is in the denominator, and for some reason, whenever the unknown's in the denominator and you've got to rearrange it, students always rearrange it wrong. If they miss the problem, it's because they rearranged the problem wrong. So you're going to solve for the second temperature. Make sure you know how to do this. The temperature should be, let's see here, 566 Kelvin. But that question asked what will the temperature be in Celsius. So you've got to convert the Kelvin to Celsius when you're done. So it'll be 293 degrees Celsius. So check your answer with that as well. Alright, we're going to look at one more law here. And it's Gay-Lussac's law. So we've got Gay-Lussac's law. Gay-Lussac's law looks at the conditions of a gas at constant volume and constant number of moles of gas. So when the volume of the gas doesn't change and the moles of the gas doesn't change, what does change? Well, the pressure and the temperature of the gas will change. Gay-Lussac's law says that the pressure of a gas is proportional to the temperature of the gas. Meaning if you increase the temperature of a gas, you increase the pressure of the gas, right? So, like, if you throw a gas tank into a fire, you get an explosion, right? There's so much pressure because you're at the high temperature that the gas explodes out of the tank, and that's always bad, and don't do that anyway. But the pressure increases as temperature increases. The pressure decreases as temperature decreases. All right. So what's the equation then if they're proportional? The equation for Gay-Lussac's law will be the proportionality equation. You've all done proportions in your grade school careers. So if you have an initial set of conditions, pressure and temperature 1, so P1 over T1 will equal P2 over, I'm getting excited, over T2. There we go. So this is your equation. Now, once again, it doesn't matter what the pressure units are, but the temperature units have to be in Kelvin. Temperature is always going to be in Kelvin for the gas chapter. So if you read a question where the unknowns and the knowns given in that question are pressure and temperature, you're going to do exactly what we've been doing. I'm not going to beat a dead horse here, but you're going to add the pressures and the temperatures in and make sure your units match. So grab this law. This is Gay-Lussac's law. All right. We have one more law. It's called the combined gas laws. I'm having problems again. Okay, combined gas law. The combined gas law combines Boyles Law, Charles' Law, and Gay-Lussac's law into one big equation. And you're going to hold the moles of the gas constant. So what is the combined gas law? The combined gas law combines Boyles Law, P1V1 equals P2V2. Charles' law said that volume 1 over temperature 1 equals volume 2 over temperature 2. And it also combines Gay-Lussac's law, which is already written here. Pressure 1 over temperature 1 equals pressure 2 over temperature 2. So, this is the combined gas law equation. All right. All three of the laws are there. I actually remember the names of the laws based on the variables using this law. So we have PV over T, right? So I can remember PV over T equals PV over T. And I actually draw a picture to remember which law is which. So I say, okay, Boyles Law. I'm going to draw pictures of chemical goggles here. So I'm going to draw a student in a chemistry lab studying the gas laws, and they have to wear their goggles. So they put on their goggles over their face, and don't those goggles look like a sideway B? Yeah, because pressure and volume, that's Boyles Law. All right, and then they go and they put the earpieces on the goggles. So they put on the right earpiece first when you're looking at this. And doesn't that look like a backwards C? Well, yes, it does look like a backwards C. And that C connects the volume to the temperature. So they put on the correct ear first, the right ear, and they get volume over temperature. That relationship is Charles' law, so hence the backwards C. And then this is so much the truth of every chemistry lab you've ever been in. If you grab a random pair of goggles, there's always something wrong with them. I call them gangly goggles. So you go to put on that second earpiece, you think everything is going great. And then you go to put it on and there's like a piece like flying off the goggle earpiece. Doesn't that look like a lot like a G? Yeah, I know this is stupid. But I came up with this and I've never forgotten it since. So the G is like the gangly earpiece, and the G stands for Gay-Lussac's law. It relates pressure and temperature. So that's how I remember the names of the laws, and I've been teaching my students that, and they really liked that, and they've been teaching their friends that. So if you like that, that might help you remember the names of the laws. You might think, why do I need to know the names of these equations? You'd be surprised how many standardized tests students have to take for certifications and entrance to certain schools. That question actually appears. According to Charles' law, what happens? So it's always good to know the names of the laws anyway, for history's sake. Now, once again, when you use the combined gas law, we've got temperature here, right? What must the temperature units always be in? Kelvin. All right, so let's look at one example here of using the combined gas law. Okay, so let's look at the combined gas law. So, example. So this question here says, if a sample of air occupies 500 milliliters at STP, what is the volume at 85 degrees Celsius and 560 torr? What? You got to read that question again, right? I know I do. I have no clue what's going on. It's because there's so much information in one statement. But that's okay. What we're going to do is we're going to read it again, and we're going to make a list of our variables, or a list of the given things, the things that we know, and the list of the things that we don't know about this gas. How do I know it's a gas? It's air. So we have air, and air is a gas. So let's write down what we're given when we read the problem again. It says a sample of air occupies 500 milliliters. 500 milliliters is a volume. So I'm going to write down my 500 milliliters. The units always tell you what your variable it is. So know your units. All right. It says the 500 milliliters is at STP. Now, we've seen STP before. STP stands for standard, what does it stand for? Standard temperature and pressure. So if we are given an STP, we're actually given the temperature and the pressure of that gas. Standard STP, the temperature, that's the pressure. The temperature is 273 Kelvin, and we always need the Kelvin. What is the pressure? The pressure is 1 atm, which is also the same thing as 760 torr. Okay? So it can be given in different units. Okay. So it says, what is the volume at 85 degrees Celsius? Wait a second. What is the volume? That means these are all initial conditions, and we're asked for a new volume. So that's what we want to calculate. We're given a new temperature, 85 degrees Celsius. 85 plus 273. Somebody help me out here. Oh, wait. I'm not in class. What's 85 plus 273? 358 Kelvin, right? Okay, because we always want to put this in Kelvin. Celsius is bad. Okay, and then we're at 560 torr. So the second pressure is 560 torr. I'm going to put a decimal there. It makes me mad that I didn't. All right, 560 torr. So that's our second pressure. All right. So notice that our pressure is given in torr. So when we use the standard pressure, we're going to use the torr pressure, 760. Okay, so let's set it up. What variables do we have? We have pressure, temperature, volume, pressure, temperature, volume. Well, that's the combined gas law. The combined gas law is P1V1 over T1 equals P2V2 over T2. And hopefully by the time you practice enough problems, you'll have that one memorized. Okay, so what's our unknown here again? We're going to solve for the second volume. So V2 is our unknown. So I'm going to do some simple algebra here. I've got V2 times P2 over T2. So I'm going to isolate V2 by multiplying by T2, dividing by P2. See how this fraction cancels out? It's the inversion of the other. So I've got T2 over P2. Multiply both sides, right? That's algebra. Okay, so that's my volume 2. I'm sure you already know how to do that. So that's volume 2. So volume 2 equals T2P1V1 over P2T1. Wow. Okay, what's temperature 2? We're just going to substitute in now. It's 358 Kelvin. What's P1? 1 atmosphere or 760 torr. And what's volume 1? Volume 1 was 500 milliliters. 500 milliliters. Okay, I'm running out of room. Divided by P2 times T1. So P2 was 560 torr. Whoops. And what was T1? T1 is 273 Kelvin, standard temperature. Okay, so V2 equals. I'm going to cancel out my units, do my unit analysis here. So I've got Kelvin on top, Kelvin on bottom. Torr on top, torr on bottom. What's left? milliliters. So my units are going to be milliliters for volume 2. Alright, so let's multiply. I've got 760 times 500 times 358 divided by, let's see, 560 times 273. Make sure you grab your calculator that can do this. Looks like the significant figures. I got 890 milliliters. 890 milliliters. And that was just a matter of doing the math. The main thing that students miss, there's two things that students miss. Either A, they don't know what equation to use. So always make a variable list and find the equation that matches what you're given and need to find. That's the first mistake. The second mistake is just rearranging the equation, the algebra. So it's not the chemistry, it's just the algebra. So make sure you take your time and solve these correctly. Alright, I'm going to give you the answers for the next two for time's sake because it's the same exact equation. And I think you need to practice, but I'll give you the answers, okay? So, for the second problem, if you'd like to do it, and you don't want me to tell you the answer, go ahead and press pause right now and work it out for yourself. Okay, but what is the second answer? The second answer is going to be 580 degrees Celsius. 580 degrees Celsius. All right, and the third answer, because it asked for degrees Celsius, we've got to convert the Kelvin back. It will be 853 Kelvin, but you'll subtract 273 and get 580 degrees Celsius. The next one asks for you to calculate the volume, and the volume at STP will be 6.87 liters. Okay, so try those out on your own. We are going to move into the next video now, okay? This is a long one, sorry.